All right, next I want to look at percentiles and quartiles. So a z-score measures a data item's position in a normal distribution. But there are other ways to measure position as well. So another measure of a data item's position is called its percentile. Percentiles often are associated with things like standardized tests or even growth. So for instance, if anyone has young children, you often take them to the pediatrician and they'll tell you the percentiles for their height, for their weight. So it's a way to compare their height and weight with other similar age children. Same thing here on standardized tests. You're comparing your score to other students' scores on those standardized tests like SAT scores or things like that. Now, as you talk about percent, the number here actually represents the percent below that data value. So, for example, something in the 95th percentile indicates that 95% of scores or data are less than that particular score. So if you're taking a test, you really want to be in the 95th percentile because that means you scored better than 95% of the other people, right? So that means 95% of the scores were below yours. If you're in the 95th percentile for height, that means that you are taller than 95% of the other people in that category. So it's the amount of the data below that cutoff point. So if n% of items in a distribution are less than a particular data item, we say that the data item is in the nth percentile. So this can be any percent. You could talk about the 5th percentile or the 90th or the 50th. You can do any percentile you want from 1 to 100. I guess 0 to 100. So the cutoff IQ score for Mensa membership is 132.8, and this is in the 98th percentile. So what does this mean? So basically it means that 98% of people have IQ scores less than 132.8. So again, this value here, if it's the 98th percentile, that means 98% are below, right? So 98% are below. So 98% of people have IQ scores less or lower than 132.8. Now, 3 commonly encountered percentiles are the quartiles. So the quartiles divide the data into 4 equal parts. The 25th percentile is the same thing as the first quartile. The 50th percentile is the same thing as the second quartile, which is also, oh no, this is a big typo. Sorry, this should be the median. And the 75th percentile is the same thing as the third quartile. So if you hear other terms like quartiles, it's the same thing as percentiles. They're just very specific ones. So your first quartile is your 25th percentile. Your second quartile is your 50th percentile or the median. And the 75th percentile is the third quartile. Now, another good calculation would be the margin of error. So a lot of times when we do have statistics and we have data on things, there is a margin of error, right? And that's because our samples are never perfect. So our goal with samples is to learn about a population. And we like our samples to be as close to the population breakdown as we can, right? So obviously you can't get everybody in the population usually, but we try to have kind of like the same ratios. For instance, if it was 40% women in the population and 60% men, then we would hope our sample would have similar breakdowns, right? So we want our sample to mirror our population as best we can. But that doesn't always happen perfectly, so there is always a margin of error in our data. So if a statistic is obtained from a random sample of size n, there's a 95% probability that it lies within 1 over the square root of n times 100% of the true population percent. And this value here is called the margin of error. So again, we may give a value in a survey or in a poll, but there's usually a margin of error, which basically says, hey, that value could go up or down by a little bit. So this table here on the left shows that a random sample of 1,000 US adults are in a random sample. 46% of those questioned that they dread public speaking. So this was activities that US adults dread, and they surveyed 1,000 adults here. So 46%, that was the most, said that public speaking was the #1 dread for them. We're going to verify the margin of error that was given for this survey is accurate, okay? So let's go ahead and find the margin of error. So the margin of error is this formula right here. And you do need to know your sample size. So our sample size here was 1,000 because there was 1,000 US adults. So all you need to do to find the margin of error is to replace your n with whatever your n is given for that problem. So it's 1,000 here. So what you're going to do is we're going to go ahead and take our calculators. We're going to do 1 divided by the square root of 1,000. And I get about 0.316227766. Again, there's a decimal point right there. And then what you do is you're going to multiply it by 100, and that gives you a percent. So we get 3.162277766%. This is plus or minus. So that becomes about 3.2% here. So that's what the margin of error would be in this case. So for instance, what that is saying is that even though they're giving you 46% here as the mean for the sample, that they believe that it could go up or down by up to 3.2% in this case. So for part B, if we're going to actually write a statement about this, what we're going to do is we're going to take the value that we're starting with, that 46, and then we're going to go ahead and take that 46 and we're going to add the 3.2%. So that's going to give us what, 49.2%. And we're going to subtract that 3.2% here. And let's see, we're going to get 42.8%. So that's what the margin of error does. It takes that center or that mean and we add or subtract with it. So our statement here could then be something like, we can be 95% confident that between 42.8% and 49.2% of all US adults dread public speaking. Okay, so that's really what that says. Now, there's a lot more background here why we use the words 95% confident. So in a full statistics class, we would go through the background there. But basically what stats is I sort of can't ever prove anything 100%. If I have a sample and I'm trying to figure out what happens with the population. I can feel pretty confident in my results, but again, unless you have full population data, you can't 100% be sure of something. So we say that we're 95% confident that it may not be exactly 46, but between 42.8 and 49.2% of people, US adults, would dread public speaking in the full population. That's what we're saying here. Now, one thing I want to note in this I thought was really helpful is that, you know, we are saying that we're 95% confident, which means that there's a 5% chance sort of that we're wrong, right? So there is a chance that we're wrong here. So when we do our surveys, when we do our data, we do the best we possibly can to collect a sample that we think is representative of the population. And then we take that sample data and we try to expand that information to the entire population, right? So we do the best that we absolutely can. But sometimes it's not perfect and sometimes it could be incorrect, particularly if you get a sample that just does not represent your population, you may not realize it. So for example, this is some things that could happen when we're doing surveys or we're trying to poll people. Sometimes people don't always respond honestly and accurately. So maybe you get a survey on the phone or something like that, and they're answering questions, but maybe you're embarrassed by your answers, so you don't really want to say how you really feel about something. So you may say that you're undecided, or maybe you make up an answer instead. You may try to be nice and respond to questions in a way that you think will make the pollster happy. Maybe you just want to get off the phone really fast, so you're kind of just giving whatever answer you think would get you off the phone the fastest. So, you know, when we do these surveys and these polls of people, we are assuming that they're giving us their truthful answer, and that they know what their truthful answer is, right? So somebody could really be undecided about something, but maybe they're giving you an answer anyway, instead of just saying you're undecided. So your sample data can really affect the outcome, right? So this is something to note that, you know, when we're 95% confident, 5% of the time, that's 1 out of 20, the error could be greater than 3.2%. That's what we're saying here, is that the error may not be just 3.2%, maybe it's bigger than this. So maybe we don't have the right range of values here, maybe we're a little bit off. So again, if you take a full stats class, this becomes explained a little bit more why this is all true. But whenever we're polling, we typically have some sort of margin of error where we feel pretty confident the population value would be between, but there's always that small chance that we're wrong and that we're off. So it's something to keep in mind. And that actually kind of happened a lot with the 2016 election. So if you remember, a lot of the polls, not every single one, but a lot of the polls were showing that Hillary Clinton was going to win the election. And obviously she did not. So, you know, people's faith in polls were, I think, a little bit discouraged. But what happens is, you know, it all depends on the sample that you get. So if the sample ended up being more heavily people who are in favor of Hillary Clinton, rather than maybe being an equal sample that represents the population, that could have happened. Or maybe people were not willing to say who they really wanted to vote for. So again, that just happened to be where our sample did not match the population. And so the polls, a lot of the polls were wrong, and we're outside that margin of error. All right, finally, we've been spending all this time on the normal distribution, but there are a ton of other kinds of distributions that are not normal, that are not bell-shaped. So don't think that all data has to follow those two, or that main picture. So not all data is approximated by the bell curve. So another type of distribution is called a skewed distribution. And a skewed distribution occurs when a large number of data points are piled up on one end of the distribution. So it's not symmetric. It kind of leans or skews to one side. And then you almost have this tail at the opposite end. So when the tail is on the right, the distribution is called skewed right. So this would look something like this. Okay, so it kind of starts like a normal curve, but you have a much heavier tail kind of running out this way. And of course, your book has a much better example of it. So what ends up happening here is your mode ends up being the peak. Your median tends to be next, so they're not all going to be the same. And then your mean, it's not really this far away, but your mean would be the next one over. And what happens is this tail pulls that mean to the right with it. So you don't have that they're all the same anymore. You don't have this nice symmetry. So your mode is still the peak, but then what happens is your median actually becomes a better center, and your mean really gets skewed towards that tail. If the tail is on the left, we say it's skewed left. So again, the picture maybe looks something like this. So again, your mode is going to be at that peak, and then you're going to have your median next, and then that mean is getting pulled towards that tail here. So you have this skewed data. And I'll just show you the book quickly because it's a much nicer picture in your book. So if you go to page 18 in your book, you can see these two skewed pictures here. And then here's the original raw data. So for instance, you know, we graph the raw data first and look at the shape, and you can see that this shape is definitely not a normal bell curve. It's not symmetric at all. This is definitely a skewed right graph, because you have this kind of, most of your data is on the left, and you have this kind of long right tail that just kind of keeps going out that way. So not every data set is going to be symmetric. And not every data set is going to be skewed either. So this is just touching on the beginning of what your data can look like, and there's lots of different distributions that we can use. So the examples that your book gave for this one up here, the skewed right, these were ages of women who were surveyed in a particular study. And what happened was most of the women who were surveyed were ages 16 to 20. So they tended to be in the late teens to early 20s. So that's why you have the majority of your data is on the left here. And then you had very few women surveyed who were older. So you have a skewed distribution. Something that could be skewed left, like the second one, could be something like faculty teaching performance in many colleges. So when you guys do your course evaluations, probably, so at some colleges, I would guess maybe a lot of faculty members get like 4s, right? So if 5 is the highest, maybe a lot of them get 4s. So you kind of have a heavier distribution here with the higher values. But maybe there's a few faculty who are getting really low scores, right? If they're really not performing well. So that could be an example of maybe a left tail distribution where most of your people are scoring pretty high, but you do have some few people who are getting really low scores there. And again, I don't know what happens at the Mount, so it could be different here. They're just the book, your book cites that could be a common example, at least in some colleges. All right, so that's a little bit about the normal curve and a couple other distributions that we tend to see. But again, we're really just touching the surface here with an introduction to statistics. And in a statistics class, we'll be going to these distributions and these pictures and this data much more detailed. But hopefully this is a nice introduction for you with a little bit about how the normal curve works and some applications we have there with the normal curve and also with standard deviation.